This lesson looks at sequences and series. A sequence is a list of numbers that follows a certain pattern, and a series is the sum of those terms. So let's look at some sequences first and see if we can figure out what the pattern is. Here's a sequence: 1, 3, 9, 27, 81. What's happening here? Well, you might notice that 1 times 3 gives us 3, times 3 gives us 9, times 3 gives us 27, times 3 gives us 81. So it's like here we've got 3 to the power of 0, 3 to the power of 1, 3 to the power of 2, 3 to the power of 3, 3 to the power of 4. Various ways of writing that. And so eventually we're going to be writing formulas for these. But let's just look at another pattern. So that pattern would continue on. What about this pattern? What's happening here? Well, it's definitely not being squared or multiplied, but from 7 to 12, we've added 5, and again we've added 5, and we've added 5, and we've added 5. So when we're adding and subtracting between each term, those are going to be called arithmetic sequences, and when we're multiplying or dividing, those are geometric sequences. But there are also other sequences as well. What's happening here? Well, this one starts with a -1, then becomes a quarter, and then becomes a 9th, and a 16th, and then a 25th. How are these related? Well, one thing that's happening is your sign is alternating, positive, negative, and so on. Now, that can be looked at as a power of -1. So let's say you had a power of -1. -1 to the power of 1 would be negative, whereas -1 to the power of 2 would be positive. And then so on to the power of 3 would be negative as well. The other thing that's happening here is this is 1 over 1. And now you can notice that 4, 9, 16, and 25 are all perfect squares. So what's actually happening is here we've got -1 to the power of 1 times 1 over 1 squared. Here we've got -1 to the power of 2 times 1 over 2 squared. Here we've got -1 to the power of 3 times 1 to the 3 squared. -1 to the 4 times 1 over 4 squared. And so on. So you could actually almost write a formula for this, and you could say, well, eventually the nth term, this was the first term, so input of 1. This was the second term, so input of 2. Third term, input of 3. You could actually write a formula saying for the nth term, it's going to be -1 to the power of n times 1 over n squared. And so what that is called is that's called the general term. So it's the an. So what is the nth term? An is used to represent the nth term, and the nth term can be given a formula based on what the nth term is doing. So can we find the nth term in these other ones? Well, here the first term had a 0 power. The second term had a 1 power. The third term had a 2 power. The fourth term had a 3 power. There's always one less. So you could say that the nth term will have 3 to the power of n minus 1 in this case. What about here? Well, this was 7, and then 7 plus 5, and then 7 plus 5 times 2, and then 7 plus 5 times 3, and then 7 plus 5 times 4. No, 7 plus 5 times 4 was the fifth term. So notice the 4 is always 1 less than. So this changing number is always 1 less than the term number. So the nth term would then be 7 plus 5 times, not n, but 1 less than n because of the pattern here. So those are examples of general terms. Now you can think of these as functions. It's like, well, if my input is n, then what's my output for that nth term? So this could be seen as a function, like function of n, like a of n or f of n. But the general term that's used for sequences where items are discrete and not continuous, meaning there's no decimals, they're just integers. In fact, they're natural numbers, as you can see in the definition. So the way that's written is an for the nth term. So let's take a look at some of these. You could be asked to find the first 5 terms of a sequence. Say the sequence is given in terms of an nth term. So this means, what is A1? A1 is the same thing as plugging a 1 in for n. So it's 2 plus 3 times 1. What's A2? Well, it's 2 plus 3 times 2. A3, 2 plus 3 times 3. And you could find the next one. So what is that going to be? Well, that's going to be 2 plus 3 is 5 is the first term. 2 plus 3 and then plus another 3. So that'll be 8. Right? 6 plus 2. And then you can see it's actually going up by 3s constantly. So this is 2 plus 9, which is 11. And you can see that this will be 14 and then 17. You could find those on your own. So it's essentially a function, but it's only for natural number inputs. So let's take a look at this next one here. So we've got an input of n, and then this thing again. So what does this do? Well, if we put a 1 in, we'll have negative 1 to the power of 1 over 1, which is negative 1. If we put a 2 in, we have negative 1 to the power of 2 over 2, which causes this to be positive by squaring it, so that's 1 over 2. Then we have negative 1 to the power of 3 over 3, which will be negative 1 over 3. And then we have negative 1 to the power of 4 over 4, which causes it to be positive. And finally, 5 will cause it to be negative. And so if you ever see an alternating sequence like that, where the negatives and positives are alternating, that means the general term has that sort of item in it as a factor. All right, let's continue. So now, this first one was an arithmetic sequence because it was adding, and geometric is when it's multiplying by something constantly. So what happens here? First term is going to be 80 times a half to the power of 1. Next term is going to be 80 times a half to the power of 2, which is 1/4. Next one's going to be 80 times 1 over 2 to the 3, which is 8. 80 times 1 over 2 to the power of 4, which is 16. And then you'll have 80 times 1 over 2 to the power of 5, which is 32. So that's going to be 40, and that's going to be 20, and that's going to be 10. And then you'll have 5, and then you'll have 2.5, or you could write it as 5 over 2, and so on. So that's an interesting one. You can see that one's decreasing, so it's getting closer and closer to 0, but it will never get there. And finally, a very well-known sequence. You can look this up on Google. It gives you some very interesting visuals quite often. The Fibonacci sequence. And the way the Fibonacci sequence works is the first 2 terms are defined to be 1s. A1 and A2 are 1s. But then, as soon as n is greater than or equal to 3, meaning you could plug a 3 in here, what that means is the third term is the same as the second term plus the first term, which is the previous 2 terms. So when you add those up together, that gives you 2. And again, if that's a 4, then this will be the previous 2 terms. So really it's defining the pattern of adding the previous two terms together. So 1 plus 2 will be 3, 2 plus 3 will be 5, 3 plus 5 will be 8, and this continues on and on. So those are a few sequences. What about if you're given the general term of a sequence and you're not asked to list the first 5, but you're asked to find, say, the 8th term or the 15th term? Well, having a general term really helps with that. So A8, you're just going to plug in an 8 in for n. It's just like a function. So let's see what happens with that. All this means is that it's positive, and then you have 7 over 9. And find a to the 15. So to the 15th power is going to stay negative, and it'll be 14 over 16. So it'll be a negative, and then you can simplify 14 over 16 to be 7 over 8. Here's an application. Say a car loses 20% of its value each year. A new car costs $24,000. What is its value after 4 years? So we need to create a formula for the value of this car after n years. So there's a pattern here. Every year something happens. It starts with $24,000. So the question is, what is its value after 4 years? So it costs $24,000 initially, so that's like 0. After 1 year, it's going to lose 20% of its value, so it's actually going to be 24,000 times 0.8 because it'll still retain 80% of its value. So that's after 1 year. After 2 years, it'll be 24,000 times 0.8 and then times 0.8 again because it's losing 80% of the previous. And you can see how that's actually going to be 0.8 squared. So then 24,000 times 0.8 after the 3rd year, that'll have shrunk 3 times, that's cubed. And the 4th year, you can see that it will be 24,000 times 0.8 to the 4. So that helps us create a formula. So let's first find out how much this car is now worth after 4 years. 0.8 to the power of 4 times 24,000. Well, look at that. It's only worth $9,830.40. That's too bad. Well, what about after n years? So what happens with this formula? The nth term is going to be 24,000 after n years times 0.8 to the power of n. So you can actually find the value of this car in 100 years, and it likely would not be $0. Interesting. Fancy that. Now, let's add up all the terms. Why not? That's called a series. A series is the sum of all the terms of the sequence. You can also have partial sum, and the partial sum is the sum of the first n terms of the sequence. Series are essentially referring to the fact that you're adding up the terms. So there's a compact way to notate these sums. So let's say you have, for example, this nth term, and all this means is that if n is 1 and your term is 1, so this sequence is actually just 1, 2, 3, 4, and so on. But this could be written in various ways. So let's just take a look at the notation. S5 refers to the fact that you're taking the sum of the first 5 terms given this nth term. This here is summation notation, and this is a sigma, a Greek symbol for S for sum. And I is the index of summation, meaning I is running from 1 to 5, plugging into this formula. So your general term is plugging in there. Usually we use n's for the nth term, but we use i's for the summation notation just to differentiate. But essentially it's the same formula. So all this is saying is plug 1, 2, 3, 4, 5 into this formula and add those up. If you just left it as the sum of the first n terms, that'd be all the way from 1 to n, which is 1 through n. And you could also consider it as an infinite sum. So maybe this sequence goes on forever. What do you think 1 plus 2 plus 3 plus and so on equals to? Well, yes, it would be infinity. So let's try to read these notations here and find the sum of each of these series. So the computer just put these here, but it's best to write them so that you can see them clearly. So I is running from 1 to 5, meaning you'll have 1 plugged in, 2 plugged in, 3 plugged in, 4 plugged in, and 5 plugged in, and all of those terms will be added. So when we plug in a 1, you'll have 1 squared minus 1. That's your first. And then you have 2 squared minus 1. And then 3 squared minus 1. And 4 squared minus 1. And 5 squared minus 1. So let's find that. Find the sum. So that's 1 minus 1 plus 4 minus 1 plus 9 minus 1 plus 16 minus 1 plus 25 minus 1. And when you add that all up, it equals 50. Try the next one. This runs from k equals 2 all the way to k equals 6. So we're going to plug in a 2, and then we're going to plug in a 3. And hopefully you can see the pattern here. This is all about patterns. And then a 4. Yes, it's a bit tedious. And then a 5. And we're almost there. And then a 6. Imagine adding up like 10 of these or more. Yes. So you can see why mathematicians have created some formulas that you're going to learn about pretty soon that help find these sums in various ways. This is a whole branch of mathematics, actually. But we're just beginning, so let's just plug through it. So we've got positive, and then 6 minus 2, and then a negative 9 minus 2, and then a positive 12 minus 2, and negative 15 minus 2. And so you can find all these. When you add them all up, you get 10. Finally, let's write each of these sums using summation notation. So this takes a bit of creativity. First of all, because we have an alternating sequence, we know it's going to be negative 1 to the power of something. And we know we're going to be using summation notation. Now, the sequence could have gone continuously further, but our I is starting at 6. So I is starting at 6 and going up to something. In this case, the numbers are going up by 1, meaning we could just actually have just the I sequence, which would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And if we started at 6, go up to 10, that gives us our numbers. However, we need our alternating bit, so we need to multiply this by negative 1 to some power. Now we need to make sure that when we plug in the power, say we have it as I, that it works out in terms of which number is negative. So if we take it to the power of 6, is it going to be positive? Yes, it is. To 7, it's going to be negative? Yes, it is. So we've got our summation notation. Let's try the next one. What's happening here? Aren't these perfect squares? So we could take our summation notation, and I is going from some number up to another number, and I is being squared. So this would mean if we started at 1, that'd be 1 squared, 2 squared, 3 squared, 4 squared. But here we're starting at 4 squared. So I is starting at 4 and going all the way up to 8 squared, which is 64. And that's it. There's no alternating negative, so we don't need the negative 1 to the power of.